Welcome to The Explainer. Today, we're going to break down the fundamental materials that make up, well, everything. I mean, literally everything around us. From the phone you might be holding in your hand right now to the buildings that scrape the sky. So let's just dive right in.
It sounds a little bit like a riddle, doesn't it? But the answer, it lies in this invisible world of engineered materials. See, each of these things exists because some very smart people chose a very specific material with a really unique set of properties to solve a particular problem.
And the secret to all those amazing properties? It's hidden right here, at the atomic level. It's all about the way atoms bond and arrange themselves. So to really get a handle on our world, we've got to understand the three great families of materials that it's all built from. And those families are metals, ceramics, and polymers. You can think of each one as having its own unique personality, its own set of superpowers. Let's kick things off with the family that pretty much forged our entire modern industrial world.
So when you think metal, you probably think strength, right? Durability, and you're not wrong. But their true power, the reason they are so dominant in engineering, is the absolutely incredible variety of alloys we can cook up by mixing different elements together.
Now, the undisputed kings of the metal world, that would be the ferrous alloys, basically anything based on iron. So think steel and cast iron. This stuff is the backbone of construction, of cars, of heavy machinery. It's strong, it's versatile, and it's relatively cheap to make. But it does have one major weakness. It rusts. And here's where it gets really cool. A tiny, invisible change can have a massive, massive impact. With cast iron, it's not just about mixing iron and carbon, it's all about the shape that the carbon takes deep inside the metal structure. This table just illustrates it brilliantly. I mean, look at how much control we have. If that carbon forms into little flakes, you get gray iron. It's kind of brittle, but it's fantastic at dampening vibrations, so we use it for things like machine bases. But then change those flakes into little spheres, nodules, and bam, suddenly you have ductile iron, which is so strong it starts to act a lot like steel. It's just a perfect example of engineering on a microscopic level. And if you really want to see the absolute peak of what metal can do, you have to look at superalloys. These are incredibly sophisticated blends of nickel, cobalt, or iron-nickel. And they're designed for one thing and one thing only, to survive the absolutely hellish environments inside jet engine turbines, where they have to withstand unbelievable heat and stress.
Okay, let's switch gears and move on to our next family, ceramics. And look, if you're just picturing coffee mugs and pottery, you are only seeing a tiny, tiny piece of the whole picture.
The classic superpower of ceramics has always been their incredible resistance to heat. They're amazing insulators, which is why we line high-temperature furnaces with them. But the real excitement, the future of this whole material family, that's happening in what we call advanced ceramics. And this is where things get truly mind-bending. Seriously, we are talking about taking simple carbon atoms and arranging them one by one into these incredible, almost futuristic structures. So first up, you've got this beautiful thing, a fullerene, also known as a buckyball. It is a perfect sphere made of exactly 60 carbon atoms, like a microscopic soccer ball. And we're already finding uses for them in everything from personal care products to pharmaceuticals. Now, take a sheet of carbon that's only one atom thick and imagine rolling it up into a perfect, seamless tube. That's a carbon nanotube. Their electrical properties are so unique that they could one day totally revolutionize electronics, maybe even the screen you're watching this on right now. And that flat sheet itself? Well, that's graphene. It's a layer of carbon just one single atom thick, yet it's stronger than steel, more conductive than copper, and totally transparent. The potential uses are just staggering, from flexible touchscreens to hypersensitive DNA biosensors. It's a real game changer. And that brings us to our third and final family, polymers. So if metals are the strongmen and ceramics are the heat-resistant specialists, then polymers are the shapeshifters. They are the most adaptable and versatile materials we have.
You know, the world of polymers, or plastics, has evolved like you wouldn't believe. We started out with stuff like bakelite way back in the early 1900s. It was revolutionary for its time, but it was also really hard and brittle. Fast forward to today, and we've engineered these complex, long-chain polymers like UHMWPE that have properties that would have seemed like straight-up magic a century ago. This really just shows how specialized these new polymers can get. So let's take that one we just mentioned, ultra-high molecular weight polyethylene. Let's just call it UHMWPE, and let's look at its superpowers. Okay, for starters, it can literally stop bullets. This is the stuff that's used in modern lightweight body armor and bulletproof vests.
It's also so slippery, so wear-resistant that it's one of the main materials used in artificial hip and knee joints. It lets them move smoothly for decades because it has an unbelievably low amount of friction.
And on top of all that, it's just incredibly tough. It can handle harsh industrial chemicals, constant abrasion, and it just doesn't break down. That makes it perfect for things like gears, bearings, and all sorts of industrial containers.
So we've gone through the strength of metals, the incredible resistance of ceramics, and the sheer versatility of polymers. After seeing these three totally distinct families, each with its own superstar materials, what's the big takeaway? I think this quote just nails it. There's no such thing as a single best material. Real progress in the modern world comes from understanding this incredible toolbox we have, and then choosing the right one, or even creating a totally new combination of them to solve a very specific problem. Which, of course, leads us to a final, really exciting question. We've gone from shaping iron to literally arranging individual carbon atoms. So as we keep designing and innovating at this fundamental level, what challenges are we going to solve next? The possibilities, it seems, are really only limited by the materials we haven't even imagined yet.